Good evening. In today's lecture, we are going to be continuing what we did last class. Last class, we started with sets, and the last thing we did is types of sets. So let's do a quick revision here. Okay. So for the types of sets, we have first empty set. Now, empty set is a set which has no elements, it's empty. A singleton set is a set with only one element. I've misspelled empty here. So a singleton set is a set with only one element. Then we have a finite set which has a limited number of elements. So if you count all those elements, you will eventually find how many elements there are. Then we have the infinite set which has infinite number of elements as the name suggests. So if you keep counting and counting and counting, there'll always be more elements ahead of you. For example, set of all natural numbers. Then we have equivalent sets, which are sets with the same cardinal number, or sets who have the same number of elements in them. So you can go through the example I've given here. Both of them have four elements. Hence, A and B are equivalent sets. Then we have equal sets. Equal sets are basically sets with the same elements. The order of the elements doesn't matter as long as both of them have the same elements. Now, we will do some questions on this. Let me take the color blue. Put examples here. All right. So, question number 1. Which of the following are examples of empty sets? Which of the following is an example of an empty set? Alright, so we have two parts in this question. Let part 1 be set of all prime numbers. Okay, so let's just make a set, represent this set in the roster form. So set of prime numbers, we have 2, 3, 5, 7, 11, 13, and it goes on and on and on. So this would be an infinite set, and hence it is not an empty set. Now example 2. X such that X is a point common to any two parallel lines. Any Alright. So as we all know, these are parallel lines. Parallel lines are lines that do not meet. So this is a line. Just this. So these here are parallel lines. Now parallel lines, the main property of parallel lines are they never coincide, they never touch each other. So hence X is a point common to any two parallel lines. This will be a null set, an empty set. There's nothing there. There's no element to the set, hence it is an empty set. Okay, so moving on, let's go to question number 2. Which of the following are finite sets or finite or infinite sets? Okay, so question number 2. diff which of the following sets are finite and which are infinite? Sets are finite and which are infinite. Right. So this again, we will do a couple examples. Example number one, set of concentric circles in a plane. Right. So this could be any number of circles. There's no limit to concentric circles. You can draw as many as you want. So hence this would be an infinite set. Fine. Now example number two. Example number two. Set of letters in the English alphabet. Set of letters in the English alphabet. Fine. So if we put this in the form of a roost, in its rooster form, we have A, B, C, D, all the way up to Z. So again, this is a finite set. Right. Let's do another example here. Let me take the color blue. 3. X belongs to natural numbers such that x is less than 5. X is more than 5. Well, if you make a set here, let A be the set. Now x is a natural number and x is more than 5. So obviously we'll start from 6, 7, 8, 9, and this will go on and on and on since there's no upper limit to this. X is just more than 5, it's not less than anything. So that will be the set. And if you observe, this will be an infinite set because there's not really an end to it, is it? Infinite set. Fine. I think this is enough for this question. Question number 3. Which of the following are equal sets? Are equal sets. Fine. So we have 4 options here. There is 1, is A is equal to 1, 2, 6, 1, 2, and 3. Then we have option 2, P is equal to x belongs to rational numbers such that x square minus 2x plus 1 is equal to 0. Right? Then we have 3, C is equal to this 1, 2, 2, 3, and we have 4, which will be D is equal to x is belongs to rational numbers, real numbers, my bad. This R represents real numbers. We'll quickly revise the points we did here. N means natural numbers, Z means integers, Z plus is positive, Q is rational, Q plus is positive, R is real, R plus is positive real. Fact. So this, in fact, is real numbers. So x belongs to real numbers such that x cubed minus 6x squared plus 11x minus 6 is equal to 0. Okay, so this is a slightly tricky one. Let's first look at the easier ones. We have a is equal to 1 comma 2 comma 3. That's pretty simple by itself. Then we have b is equal to b is a real number such that x squared minus 2x plus 1 is equal to 0. Alright, so first we'll solve b. Let's scroll down a bit. Okay, this is as far down as I can go. B is equal to x belongs to R such that x square minus 2x plus 1 is equal to 0. Fine. So let's solve this quadratic equation here. We get x belongs to R such that if you see this is x minus 1 whole square which is equal to 0. We get the values of x as x is equal to 1 comma 1. Fine. I'll write down the identity here. A minus b whole square is equal to a square plus 2a square minus 2ab plus b square. So I'll put that in a box. Okay, good. Now on with the question. We got x as 1 comma 1. As you can see, that is clearly not the case here. We have uh, A and B will not be equal sets. Okay. Now let's move on to C. Now I'll take the color green again. C is equal to 1 comma 2 comma 2 comma 3. As you can see, 2 here is redundant. We can shorten that, so we just get 1 comma 2 comma 3. Now A and C, if you look here, A and C basically have the same elements, so they are equal. Okay, so now we have A. Till now we have gotten A is equal to C. A and C are equal sets. Now let's work out D. Now D was okay. D was x belongs to real numbers such that x cubed minus 6x plus 11x minus 6 is 0. This is going to be a slightly longer one. X belongs to real numbers such that x cubed minus 6x squared plus 11x minus 6 equal to 0. So let's do it the other way around. Fine. We'll start by taking values of x. Now if x is equal to 1, we get this as 1 minus 6 plus 11 minus 6. So 1 minus 6 plus 11 minus 6. Minus 6 minus 6 minus 12 plus 1 minus 11 plus 11 is 0. So we get one value of x as 1. So this is true. And if we take x is equal to 2. Now for x is equal to 2, we get it as 2 cube is 8 minus 24 plus 22 minus 6. So 22, 24, 6. We get it as 0 as well. So this is true. Fine. We'll do 3. X is equal to 3. Now 3q27 minus 54 plus 33 minus 6. 54, 33, 27. Okay, we get this as 3 as well. Fine. So D will be equal to 1, comma 2, comma 3. Alright, then we have A as 1, comma 2, comma 3, C as 1, comma 2, comma 3, and D as 1, comma 2, comma 3. So hence A is equal to B is equal to C is equal to D. This is our right answer. I'll make a box, then we can move on to the next question. Very fine. Now the next question would be uh, from the sets given below, select equal sets and equivalent sets. Okay, this will be a slightly larger question. I'll scroll down, or I'll do the question right here, right beside it. Fine. Scroll slightly up, make a line here. Take the color green. Where is green? Green. Fine. So this is question number 4. I found question number 4, right? Question number 4. From the sets given below, select equal sets and equivalent sets. Select equal select equal and equivalent and equivalent sets. Fine. So we have these sets here. Let me write that down. We have A, which is equal to 0, comma A. So this is 0. Then we have B. B is equal to 1, comma 2, comma 3, comma 4. Then we have C. Now C is equal to 4, comma 8, comma 12. D is equal to 3, comma 1, comma 2, comma 4. E is equal to 1, comma 0. F is equal to 8, comma 4, comma 12. Then we have G. 1, comma 5, comma 7, comma 11. 1, 1, comma 5, comma 7, comma 11. Then we have H is equal to A, comma B. And so let's first scout for equal sets. Okay, let's scout for equal sets. Do any of the sets here have it? They do. Now B and D are equal sets. Can you tell me why? It's basically because B has has the elements 1, 2, 3, and 4, and D has the same element just in another order. Hence, I'll write it in red here. B is equal to D. Fine. Then let's look for more. We have C and F. C has 4, 8, 4, 8, and 12, and F has 8, 4, and 12. Again, same elements, different order. So I will write C is equal to F. Do I see anything else? Do I see anything else? No, these are the only equal sets. Now we go to equivalent sets. Now equivalent sets, as we discussed earlier, basically sets with the same number of elements. So if we look at it first, let's start with 2. Now A, E, and H have 2 elements. So in a way, is equal to n of v is equal to n of h. Now this is basically how you represent cardinality of a set. Cardinality is nothing but the number of elements that are in the set. Number of elements in A is equal to number of elements in E is equal to number of elements in H. Fine. Now let's go for element sets with three elements. We have C here, C and F. Only C and F have three. Okay. We have C and F. So n of C is equal to n of F. Fine. Now let's go for 4. We have B with 4, D with 4, and G with 4. Fine. So n of B is equal to n of G is equal to n of F. Fine. So we have all the answers here. We have the equivalent sets right here. I'll mark this in another color. Come on. Blue select. Okay. We have equivalent sets right here. Now we have equal sets here. And these are equivalent on. Okay. So we get the idea. We got the answer here. Now we will move on to subsets now. We have spent a lot of time solving questions. Subsets. Fine. So what are subsets? I'll write the heading here. Let's write in which color should I write in? I'll write in blue is a very pleasant color. Fine. So subsets. Fine. Now let for example let A and B be two sets. Now if every element of A is an element of B, then A is a subset of B. Now let's assign some values here. Let A is B2, 4, 6, and 8. Whereas let B be 1, 2, 3, 4, 5, 6, 7, 8. Now if you see A has 2, 4, and 8, 2, 4, 6, and 8, and B has all those elements, but and then more with them. So since all the elements of B, you can find all the elements of A in B, we write it as A is a subset of B. Yes, we write A is a subset of B or A is contained in B. I'll write the notation here is a subset of slash is contained in. Okay, good. Now let's revise this concept. This is a very crucial concept we use throughout maths. Subsets now. We have A. A has 2, 4, 6, and 8 as its elements. Now if you look at B here, B has 1, 2, 3, 4, 5, 6, 7, and 8. Now all the elements of A, you can find those elements in B somewhere. We have 2 there, we have 4 there, we have 6 there, and we have 8 there. Now A can completely nest itself within B and you won't notice any difference. Now in such a situation, you denote it as A is a subset of B, and that representation there, you can read it as a subset of or is contained in. Now we just introduced the concept of subsets. Now the existence of subsets also implies the existence of supersets. Now supersets are basically larger sets which have the elements of another set in them. So in this case, B is the superset. I will write in another color here. A is the subset and B is the superset. Now, if I want to denote that B is a superset of A, I just write it like this: B with. We write it as B. If I could find my cursor, B is a superset of A. Fine. Is a superset of, now that is just that's enough. Okay, is a superset of, fine. So that is a pretty straightforward concept we did here. It's very important. We will use this throughout maths. Now let's write some theorems on this. Now theorem number one, I'll write this in red and I'll put this in a box as well. Well, theorems. Now, theorem number one is every set is a subset of itself. Every set is a subset of itself. This is one. Now let A be any set, then each element of A is clearly inside A itself, and hence we can say that A is a subset of A. Now that was pretty simple. Now we'll move on to Now we'll move on to theorem two. Theorem two being the empty set is a subset of every set. Empty set is a subset of every. Fine. Again, this is pretty self-explanatory. An empty set is a set which has literally no elements in them. That's what the name suggests. Empty set. It's completely empty. Now, if you have a set like A is equal to 1, 2, 3, 4. Fine. We have these four elements. Pretty simple. Now, an empty set. Em- Emptiness resides everywhere, all right? So if you have any set in it, if you have any set in general, you will always find an empty set in it, because empty sets, they don't need anything within them. They can just pretend to be there in the corner. If you visualize it like that, we have a room full of people, and people are getting ordered one by one, but there's always nothingness at the end. There's always a void at the end. Now that void is represented by the empty set. Okay, this gets pretty tricky if we move on further into the chapter. So it's better to just implant this in your brain that an empty set is a subset of every set. Now, the third theorem we have is the total number of subsets. See, total number of subsets of a finite set of a finite set contains n elements, containing n elements, containing n elements is 2 to the power n. Okay, so let's take the example of A here, the set we defined earlier, A. We have A as 1, 2, and 3, 1, 2, 3, and 4. Now it has 4 elements. So if you take 2 to the power 4, which is 2 into 2 into 2 into 2, basically 16. Yes, basically 16. Now what if we have to represent this set? So subsets of A or power sets of A is 16. Now the number of subsets a finite set can make is called its power set. So power set of A is 16. It can make 16 complete sets. Now let's try to list those sets. We have individual numbers. All right. So scroll down. We just have one. Then we have two. We have three. and then we have 4. Fine. Now we can start making combinations. We can have 1 comma 2, 1 comma 3, and then 1 comma 4. Fine. We have 1 comma 2, 1 comma 3, 1 comma. I should have chosen a shorter set. This is going to take forever. Fine. Now let's start with 2. Now 1 comma 2 is very different from 2 comma 1. No, it's sorry. 1 comma 2 is not different from 2 comma 1. Again, as we saw earlier, these are basically the same elements, just in a different order. That does not matter. Fine. So we have 1 comma 2 here. Okay, so we see 2 comma 1 will be done. So let's just start off with 2 comma 3. We have 2 comma 4. Then we have, if we see 3 comma 1 will be done, 3 comma 2 will be done. We only have 3 comma 4. Okay, now let's move on to pairs of 3. So I'll have 1, 2, and 3. I'll have 2, 3, and 4. I will have, let me see the set again, slightly above. I will have 1 comma 3 comma 4. Then how many do we have now? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. Okay. Now the next one we'll have is, let's make it. Do we have 1, 2, and 4 somewhere? We have 1, 2, and 3. No, we don't have 1, 2, and 4. Fine. Can we make any other sets from 3? 3, 4, 2. We have 3, 4, 2. 2, 3, 4. 2, 4, 1, and 2. Okay. Okay, we got. Then I think we have covered all 3 element sets. Let's go to 4 element sets. We can only make 1, comma 3, 2, comma 3, comma 4. Now, if you count this, this will be 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. But according to the formula, we should be getting 16. Now, that very last set, if you go to theorem number 2, an empty set is a subset of every set. So, as you have probably guessed by now, the last set is an empty set. There is always a void in any well-defined set, that being the empty set. So now we have 16. Fine. Glad to have gotten that out of the way. Can I zoom out here? Yes. Let me put this within a red box. Theorems. Fine. Zoom back in. Okay. Okay, so that's it for today. This is where we'll be leaving this. From next class, we will start intervals as subsets of R, and we will do some examples along with that as well. Thank you.